Alright, time for another DraftPhysics.com video presentation. Debate physics also, but no one to debate, frankly, on the subject. Sure, people are willing to debate things, but not physics subjects. So, we're back to the lever experiment, and I'll play later some PhysicistMichael clips that demonstrate that he got more than one prediction wrong in his lever experiment. And so again, I'll defend what I've claimed to be shenanigans in terms of dishonesty, and frankly. And so Ian.Gostling made this particular video to claim that somehow my accusations aren't appropriate or deserved or earned or credible or all of that mush. And so I'm just going to re-emphasize the point. Okay, so he hasn't done any follow-up, so we don't know if he's going to do more experiments here than just leave us with nothing, pretty much. So we'll have to see. No information provided. And I'll just read a PhysicistMichael comment that he's left on this video, and then point out how it's just obviously dishonest. His statements aren't true. All right. So he says, looks like a good setup. So it's not a very good setup. He has no way to measure velocities, which is a downside. And it is kind of rickety, but whatever. And demonstration that the springs, so he's saying this demonstrates something, which is very surprising because it demonstrates exactly what I predicted. So in some way, how is this a good demonstration? It perfectly matches what I predicted would happen. So how is this good for their side? So again, it's just so dishonest. He's claiming a victory when it's a complete defeat of his original prediction. His original prediction was the other object only leaves with half, and there's half the energy is reflected by the spring. That's his prediction. So, I mean, Ian, how are you being honest to complain about my complaints about dishonesty when he's claiming this matches his prediction essentially, when it clearly doesn't? Are you going to tell me that's not the truth? I mean, do I really have to play the clips over and over again or something? I mean, when do you concede that this isn't an honest description? All right, so he says, good setup and demonstration that the springs and direct collision have similar performance. Okay. Similar, but not the same. And again, why, if they have similar, if you're going to concede that it's close enough, then why not just do the experiment without the springs? Why keep including them on purpose? Okay. To determine the theoretical losses, so again, those are pretty easy to determine. I mean, frankly, whatever you're not getting on the other side of the lever is what you lost. From the bar, we just need the masses of the two objects and the bar. So I don't even know why you would need the masses of the objects when the bar is the only thing that you're going to be counting as a loss. So how much energy it takes to move the bar, okay, is calculatable, but it's observable. So why not just observe it instead of calculating it? And the bar length and the distance at which the masses hit. So all of that doesn't matter to how much you lose to the bar. But anyway, if you want, I can send you a copy of the Excel calculator I used in my video, where you can just plug in the values and get the predicted values. And again, who cares? You know it's going to be a certain amount of energy lost to moving the lever. So what? Again, I mean, you know it's going to happen. You're going to see it happen. You know it happens, and so you just calculate it out as always being the same. So if you're hitting with the same force on the lever, and you're going to give the bar the same amount of force as a percentage, then what do you need anything else for? All right, I had an email, blah, 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 blah. The hard contact case didn't work. It's okay, so this is where he's going to tell a story again. And it's, you know, how believable is this one? Didn't work in my setup because I didn't have a good way of mounting the rigid bumper. So he said he used a bolt, a rounded screw or something. where I was confident it wouldn't damage the cart on impact. So again, the idea that he's a physicist and he can't figure out how to disperse the impact across the surface is kind of, you believe that? You couldn't figure out like a block of wood or something else, just put something that won't absorb too much energy but can, if it has to, prevent you from damaging one part. Just all you need to do is spread the force across a larger surface. I mean, that's not that complicated. The methods I tried were not much better than the spring. So again, he's saying it's not much better in what way? So the truth is his predictions were way off. Okay, so when, I just played his prediction video again. I didn't realize how far off he was. He wasn't even doing the 1.4 thing. He was saying something even more dramatic in terms of the loss of energy that you could expect going the opposite direction. So he says weren't much better than the spring. Much better at what is the question. Okay, and were more difficult to align. So these are all just little minor complaints, frankly. This isn't that difficult. You're just saying your cart is the wrong shape. You want to change the shape of the front of the cart so it impacts a lever more directly. I mean, that doesn't seem at all complicated for a physicist. And I figured using the carts and sensors was more important for getting accurate velocity data. So I don't know what the sensors... Eliminate not using the carts at all just because you can't figure out how to put a point on the cart. I mean, that's what he's basically saying. I mean, he had to resort to putting clay on it because he couldn't think of any way of applying any way to make it so it's not going to damage his cart. Now, you could argue that if I just put a piece of plastic on front of the cart, the plastic can't do much damage. I mean, it's kind of impossible. And it's rigid and firm enough where it's going to be elastic enough where you're going to transfer the energy. So he could have used almost anything, would have worked. So this is just kind of a bullshit. And if the springs and without the springs, when he did the hard contact, if the results were the same as the springs, that would have been evidence in his favor. And it makes absolutely no sense that he didn't video that. All right. Let's be frank. So there is no frankness here. No setup is going to change the mind of someone who, and then he does this. So this is his argument is that somehow I'm not accepting their brilliant and fantastic evidence. Yeah, and I won't accept any evidence. So, and I would just reverse this argument and say some people think the Shroud of Turin is an actual piece of geological evidence or historical evidence. And, the fact is that no, it's a big painted fraud. Okay, it doesn't have anything to do with anything real. It's not part of the real story. It's not nearly old enough. It's not all these things you can find wrong with it. And I'm supposed to believe. And that's all these assholes are doing. They're sitting there saying, I'm going to do a partial experiment poorly, and then I'm going to claim you're ignoring my great evidence, when it's not great evidence. And the fact is, part of your evidence proves your own theory wrong. Your prediction was wrong. That's a flat-out plain fact. And you're claiming that somehow I'm not accepting the evidence. Well, it seems that you're denying a piece of the evidence. The part where your prediction is completely wrong and you gave us no analysis explaining why you were wrong. Why you misinterpreted the data. Misinterpreted the experiment and somehow got your prediction wrong. Why is the lever capable of taking the energy this way and converting it into energy that way successfully when you said it couldn't? You flatly said it couldn't happen. And it did. So this is so dishonest. So again, Ian, you think this is fair. He's doing something, this is a perfectly reasonable thing, this accusation that somehow I'm denying this great, perfect evidence. Again, I had to point out to you that you did an experiment where you had the numbers way off, and you did the experiment and called it a proof. You think that's what you should have done? You should leave a video up that says proof of when, yeah, you did it wrong. Fact. And then when you did it with the right numbers, it came out exactly as I predicted, and you didn't like that. And you made a video saying, look, it came out Gary's way, and that obviously can't be true, so we have to find a reason why it didn't work. I mean, how duplicitous. Again, this is such duplicitous hypocrisy. You're making an accusation against my willingness to accept evidence when you don't have any willingness to accept the evidence. And the fact that this all should have been done, none of us should. The fact that you won't even admit your physics should already have these answers. That in 2023, we shouldn't have to have an argument about what levers do. It should have been already well established what levers do and what gears do and what hydraulic systems do. This should all be known already. All right. 1. It is absolutely certain they are correct. The fact that I think I am a rational person and I believe things for rational reasons. And so if I was on a jury, I wouldn't say guilty unless I was sure they were guilty, or I wouldn't say innocent unless I was sure there was reason, or not guilty. I wouldn't say not guilty unless I thought there was good reason to think not guilty. So again, you're just making an accusation that somehow I'm not judging your evidence correctly. I'm not totally impressed by it, when I've already made it clear why I'm not impressed. I mean, I made it clear for 2 years what the experiment was supposed to look like that I was for, and you didn't do the experiment I described, and then you're saying I should accept your results, even though it's not the experiment I wanted to have done. I mean, it's just so bullshit. And then 2, he says, lacks any reasonable methodology. So every video I make, I'm explaining exactly what I think the mechanism is. I've pointed out that the deceleration on one side, the lever, that's the great advantage of this conversion device, the lever. You can convert the deceleration on one side, the speed of it, into a faster speed of acceleration on the other side. So the half mass can accelerate faster because as far as the other weight is concerned, it, weighs less. And it can move it faster. So again, so dishonest. All right, so every video has these explanations in it for critically assessing whether their ideas actually are reasonable. So I've made these 5-minute videos explaining each one of these subjects, pointing out why I believe what I believe and what evidence I think demonstrates what I believe conclusively. And these cowards who talk this shit won't play those videos and explain where my reasoning is wrong, or where I have been unreasonable in that reasoning, that I've committed some crime against the truth. All right. I mean, these are bullshit accusations from a guy who, again, you can point out how there is no being frank here. This isn't honest. Okay. He's a weasel. All right. Those more general methodology and assessment issues would need to be corrected. So I need to correct my videos, even though my videos explain it and explain it in detail and in different ways over and over again, explaining why I believe what I believe and what evidence compels me to believe what I believe. I mean, the very fact that you have zero evidence indicating anything, it ever takes 9 times the fuel to go 3 times as fast. The fact that you have zero evidence that that ever happens and you claim it with this confidence, how is it unreasonable to say, no, I think that's reason for doubt? Or at least lessened before any progress can be made on specific claims. So again, what the progress would be the interaction. The progress would be that you make a counterclaim. So I say the Dechatelet clay experiments are bogus, and I explain the reason why they're bogus. That they're not going to tell you how much energy something has. You can't use round things denting clay as a way of measuring energy. Just as you can't use rolling an object on a friction surface as a way of measuring its total energy. Because, frankly, friction isn't linear. The faster you go, the less friction there is. These are facts I'm asserting. Your counter-argument is what? Where have you proven that friction is linear? That the faster something goes across the scale, it still weighs the same. No matter how fast I move it across the scale will read the same amount. Where did you show that or prove that? Well, that's right, you didn't. I mean, this is so dishonest. Our units of G equals 9.8 meters per second squared, where, again, I'm just resorting to the fact that the guy who invented the formula, which is Newton, And he certainly didn't think it's per second squared. He thinking it's 9.8 per 1 second, 1 unit of time. Not 6 units of time, not squared units of time, not any number of units of time. No, it's only 9.8 if it's 1 second. If it's some other amount of time, it's some other number. It's not 9.8 anymore. That's a factual asserted claim. And what's your counter argument? That it is multiple seconds, that it can be any amount of time. It's 9.8 per whatever amount of time we say. Where's that counter evidence coming from? Where's that counter argument been made? Nowhere. This is so dishonest. Or momentum having direction. So clearly, yes, that's a huge difference in our model. And your model fails. On this very test that Ian's showing, your model completely fails to get the right answer because it doesn't think direction can be changed without adding energy. Okay, or anything else. Otherwise, any disconfirming evidence, whatever that even means, is just evidence confirming cheating, error, conspiracy. So again, he's wrong. He won't account for being his predictions were wrong, and yet he's claiming that somehow, he's pretending that somehow it came out his way and didn't come out my way. When, no, the truth is it didn't come out your way and it didn't come out my way. Okay, in total. Neither one of us succeeded in getting an experiment that confirmed anything completely or incompletely. So it was just useless, as I stated. Because you didn't do the experiment you needed to do. And you didn't do it the way it needed to be done, which is to recognize that there are variables that mean you have to adapt to those variables. That the amount of energy the object is in fact moving the lever, and that means the lever, you have to adjust your distances to account for the fact that you have less energy going in because some of the energy got used moving the lever itself. I mean, those are, again, that's a factual claim I'm making, that the energy to move the lever has to come from the object that you're trying to exchange the energy. You're trying to take the energy from this object and put it into this object. Clearly, you're trying to do it from a mechanism that's going to take some of the energy. So you can't have the expectation that this is going to obey the same rules as this, because frankly you're going to be putting less energy into this, and you have to account for that. Alright, so those are those arguments. So yeah, Ian hasn't responded and yet to that comment, but we'll see. But again, it's just bullshit. So all this so far is just bullshit. In terms of these statements being made that somehow the experiment was some grand success and it proved you right, and somehow I'm pretending or I'm ignoring the huge success of your experiment when it wasn't a huge success. And clearly this experiment is a huge failure for your team and a huge success for my team. My team wins, your team loses. Fact. And you're pretending it's some other way? That something else is demonstrated by this experiment? Again, I never claimed that the experiment with springs is going to be meaningful, except in the circumstance, okay, where you have some difference in the distances, that distances aren't quite right. The spring is going to show it by reflecting the energy, and that's the last thing you want to do, is reflect the energy. So anything that causes reflections is not a helpful variable. I mean, so that's on the record. I mean, all the things I've said there are videos. I mean, I can replay them for you. It's just amazing that they can keep making this assertion. All right, so I'll play the physicist Michael video again, and we'll just go over the fact that his prediction was wrong about this particular experiment first, the simplest experiment. And his other predictions were way off also. Alright, so this is the physicist Michael before the lever experiment discussion about predictions.
We're going to have to, pick something that we're actually going to measure, because we can't measure everything in the universe.
Yeah, let's just forget about relativity arguments, and let's just point out that, okay, we have one thing that has energy in the system. I can have a firecracker, I can have an object moving. I don't know what the problem is. We're saying that's the source of the energy, and we're just going to follow that energy. We just want to know what that energy does.
So yeah, so he tried to keep making this complicated about angular momentum, all kinds of other crap, and the simple experiment is you got energy going into this box, this experiment, and you just want to see what energy comes out. Not that big a mystery.
Is that a good enough thing? If I shoot a bullet at a brick wall, I just want to know what the bullet does to the brick wall. I don't have to evaluate anything else. I just want to follow the energy.
Okay, and that might be a point where our two models differ, because in momentum, if we can say we've only got internal forces, this is one of the things that I was kind of highlighting with Newton's Principia.
So he says there's some sort of experiment you can do where you can do a momentum experiment where there's only internal forces, which would have to be in perfect space where you have two objects interact with each other, because there's no other place on Earth to do that. Because every place on Earth is in atmosphere and in gravity and involves the ground in some way or another. So all of these experiments would be non-useful as experiments by his definition, because somehow there's this exclusion that you can't count an experiment. You can't count on any observation you make because there's some sort of external influence.
The argument is if there are only internal forces, like just forces between these two objects, in that case, we can use this conservation of momentum. And
I'll give that to you, frankly. Okay, I mean, I'll give you. I'm just saying, I'm not going to agree to some.
So I'm sitting here agreeing, and I thought we agreed, but we're really disagreeing. He's saying the fulcrum is an external source. Okay, so it's not an immovable object. It somehow is actually moving. We just don't see it move because it's tied to the Earth, and we move the whole Earth. So by doing this lever experiment, we did in fact move the whole Earth, and there's all kinds of external things happening to this experiment. When no, I'm arguing that the fulcrum isn't moving. Certainly not relative to any of the objects involved in the experiment. It's not moving, and you can have an expectation that any motion you put in will come out as motion in an object. We're not losing it to heat. We're not losing it to some microscopic losses. His only claim is that we're losing it to some gigantic loss, which is we move the whole Earth. Which, I mean, I shouldn't even have to argue.
Unending proposition. So if you're just going to tell me that we're just going to deal with these two objects as the experiment, I'll say fine.
okay.
So he said okay to that when he's saying exactly the opposite. He won't agree that all we have are two objects, and we're going to discount the fulcrum and the lever as much as possible. We're going to say, okay, yes, we lost some to moving the lever, but certainly we're not going to argue about whether the fulcrum moved the Earth.
Right. So my argument as to why momentum, linear momentum, isn't going to work for this thing is because at this fulcrum point, that is attached to something. That's attached to the Earth. And when this mass hits, there are going to be forces at that fulcrum point.
So again, because they don't really understand how force works, that is, they don't understand how this hits this and gives its energy to this. This is like money. Energy is like money. And all you can do is dispose of it. Okay, that's all you can do is move the dollar. Dollar bill is in the economy. It goes from this person, goes to that person. It just moves through the economy. It can't be created or destroyed. That kind of simple argument. And you're just giving the money. He doesn't have that view.
Have a fulcrum, this bar is just going to be knocked downwards out of the way. Something is holding that in place. There is a force there.
So that's not even going to happen in space. So if I hit the lever, if there's a bar in space and I hit it at far end, it's not going to just hit the bar and move it. It's going to start rotating it. So it's always going to rotate around the center of its mass. So the more mass it has, the more complicated the motion is going to be. But frankly, it's not going to just hit it and move it.
And that would be a force external to the system. It's very similar to what you've kind of mentioned with the Newton's cradle and it hitting the wall, saying, is that momentum, where does that momentum go? Is it just transferred to the Earth? And I'm saying, yes, if that thing...
So he's actually saying it. Now, Professor Lewin doesn't even say that, frankly, which is sort of surprising. I mean, in the comments section, Professor Lewin was explaining his unopened, the question he left open and never answered in any of his lectures. Is what's the nature of this momentum that you've given to an object that isn't moving? So I hit the brick wall doesn't move. I'm supposed to believe it has gained twice the momentum even though it's not moving. So it doesn't have any V at all, and yet I'm supposed to believe it has momentum even though it doesn't have any V, because the assumption is the whole Earth is moving. Well, he doesn't even say that.
is connected to the Earth and you make that hit, that momentum would be transferred to the Earth.
Okay, I mean, you can make that argument. That's fine. I'll just make the counter argument that it doesn't happen, that there's no way the fulcrum can tell the difference between the light object on the far end of the lever and the heavy object. It just feels a weight.
So whatever it's going to do relative to the one circumstance where you have even weights, it's going to have to do when there's uneven weights because you've changed the distance, which means you've changed the velocities. So that part doesn't seem to be. It seems a pretty rigid accusation I'm making about assertion I'm making about how this has to work. Regardless of what the fulcrum's doing, because the fulcrum can't feel there's a difference. It's getting hit with the same force. What's on the other side of the lever can't change what the fulcrum is feeling. So even if I accept that the fulcrum is doing something, it's going to be doing the same thing in both circumstances, so why should I worry about it?
Both 9 pounds to the fulcrum. The fulcrum can never discern the difference between the 9 pounds that's real and the 9 pounds that's artificial.
So there's a point where our two models differ. So we can kind of say that. And again, these experiments are, again,
So let's understand. His first prediction is that if we have even masses on the lever from even distances, this comes in and reflects with half the energy, and this leaves with the other half of the momentum. So the momentum comes in, half the momentum comes back as a reflection, the other half of the momentum comes back as a reflection, so you get the full momentum is exchanged not from one object into this object, and instead the momentum is reflected in both objects. His assertion was wrong. His prediction was inaccurate. It didn't match the experimental results, and he takes no account for that mismatch.
The way I approach this is we've got two models, and those two models, we're trying to make the predictions for some experiment. And then
right, and your prediction completely failed on the simplest experiment you could do with the lever. It failed completely, decisively failed.
Those two predictions are different. We're going to actually do the experiment to see which model matches the data. Is that something that you agree?
Yeah, I'm just saying.
So he's saying, do you agree to that when that's not what obviously you just want to prove my model wrong. You don't want to accept when your model's wrong. So, I mean, your duplicity and hypocrisy is obvious. You're saying that any time my predictions are inaccurate, my model has failed, and yet you won't say when your predictions are inaccurate, your model fails. I mean, it's just obvious duplicity.
Obviously, the experiment needs to be done. It should have been done 350 years ago.
So this is a good point I just made. Everybody should be able to agree. Everybody in this conversation, if they have any integrity and honesty, should be able to say, yes, I mean, physics should have done these simple experiments in 300 years. I mean, for all the experimentalists, all the stuff going on, the fact that we don't already know the answer to these questions is ludicrous. It's silly almost. It's so funnily, preposterously missing from the science. I mean, that they haven't done the simplest possible test you could possibly do. I mean, come on.
So the fact that these simple experiments have never been done, that we can't already know in advance what the answer is almost kind of funny, right? I mean, it's almost ludicrous that we have to now in 2023 have a discussion about what a lever does. So it's just kind of a miraculously bizarre fact.
I disagree on that. This experiment hasn't been done, but
okay, so he disagrees this experiment hasn't been done. He's had time to research and find out. So, but so again, Ian, are you going to say he's being honest? He's claiming it has been done, that he disagrees that this isn't missing physics, when clearly it is missing. It is something they haven't done, they haven't documented, because it can't be found anywhere on the frickin' internet.
I don't have any references on hand, so
I don't have any references on hand, like he has them somewhere. There are no references. If there were references, why wouldn't we be using them right now? Why wouldn't he use them to his own defense if he had any references? In all of this discussion and all of this argument, why wouldn't those references have come to light, and then we could just use those references? So again, the fact that you people are so dishonest that you can't even admit this is a huge oversight, that physics should have sewn this up. They should have filled this hole. They should have paved this piece of road. They shouldn't keep talking about what the truth is without actually doing the frickin' experiment.
We're just going to focus on this experiment that we're going to try to do on it. So that is my reasoning, where in my model, using conservation of momentum is not going to work because there's this force at the lever, and that's going to change things.
So some sort of nonsense force, in my opinion, okay, because it doesn't really exist, because the fulcrum isn't going to move. It's an immovable object. It can only reflect the energy or break something. You can throw something at the brick wall. It either bounces or it breaks, but that's the only two choices. You either break the wall, you break the object you threw, or if you don't break them, then they're going to have to bounce.
Also in my model, if this object is moving downwards and this object is moving up, in my model, momentum direction matters. If I have one object with a momentum going downwards and one object with a momentum going upwards, that literally can't be the same momentum.
So literally then, what is it? That's the Earth pushing back or something? What the hell is it then? What the hell, where did it come from? So again, I mean, Ian, you're going to tell me I'm being dishonest by saying, well, clearly it doesn't match his prediction. And clearly, you really think that's true. You really think that the momentum going down and this momentum on the other side, the lever is obviously doing exactly that. It's converting the direction. I mean, that's the whole point of it. It's pushing on one way and it pushes the opposite way on the other side. It's exactly what levers do. It's exactly why they have mechanical advantage. It's exactly why they have a function, is because they do that simple change in direction.
Because they have different directions. I know your model says differently, so again, we're just trying to identify differences in our model.
Right, so in my model perfectly predicts that, yes, you put the energy in this side, you step on this side moves in the opposite direction. That's what it does. All right, so I win again. My prediction's a lot closer to the actual truth of what levers actually do, which is take energy on one side and push it on the other side, going the opposite direction. That's exactly what they do.
So what we...
Well, I was going to say, I mean, could you apply that to the fact, will you agree that it will oscillate, that this lever in gravity will oscillate if I poke it? If I poke it with energy with a 5 mass at the extreme and a 10 mass at one distance, will you agree that it will oscillate perfectly?
All right, so this question is only answerable by where the fulcrum is. So if the fulcrum's in the bottom, it won't oscillate. If the fulcrum's at the top, that is, if you're attached at the top and you're balancing the lever with an attachment at the top of the lever, it will oscillate. If the attachment is in the bottom, it will just fall. So that's a subtle fact that had to be learned.
I agree that it will, if we have this system set up, so we have a bar, here's the center.
So the center is the key argument. But a little bit above the center, it works fine. Below the center, it doesn't work. So that's the point. The point is the lever itself has to be below the fulcrum for it to balance. And it won't balance if the fulcrum is below the lever. And it will balance if it's above the center of the mass of the lever.
We have a 2 mass here and a 1 mass here. I agree that if we poke that, it'll start rotating with a constant rate because there would be no net torques. Those two torques would balance out. But if you're talking about oscillating back and forth like this, in my model, something would have to be a little bit off axis.
Right, well, I can tell you I have a video on my...
So off axis would mean that, yes, the fulcrum, I'm hanging it from above rather than from, I'm applying the pressure from a point higher than the center of mass of the lever.
Channel where I do the actual experiment and it oscillates perfectly hundreds of times, like maybe 50 times, and it just goes up and down, and so
send me a link.
So this was annoying in the sense that the point of the argument wasn't about whether levers are capable of doing this. The point is that the fact is that the 1 mass and the 2 mass are both oscillating on the lever with the same momentum and different kinetic energies. The 2 mass has less kinetic energy than the 1 mass, and it's oscillating, which says there is a problem with one of the two theories. Obviously, the kinetic energy theory has a problem explaining how you can have more energy in an oscillator. The oscillation requires the energy to move from one object to the other object. How can it possibly, be twice as much energy when it's on one side, and then it's half as much energy when it's on the other side?
Send me a link and I'll have a look at that. So what we need in this case instead is conservation of angular momentum.
So this is the part where, again, it's all sideways. What does angular momentum have to do with any of this? These are carts that have to go in straight linear lines. So again, it doesn't even applicable. It's not applicable to the drawing. It's certainly not applicable to what he knows this experiment's going to be, which is on carts that have straight line track. There's no angular momentum involved for the carts.
Angular momentum. And basically, if I'm looking around some axis, angular momentum will be conserved if there are no external torques. So this is conserved if no external torques. This is
Which again doesn't say anything. It's a non-existent experiment. You can't. There's no place you can have no external torques on Earth. So again, what's the point of that condition? Because that condition can't be an experiment done on Earth.
very similar to the model of momentum, where linear momentum will be conserved if there's no external forces. It's a very close analogy in these two parts of the model.
So
So
if there was any kind of analogy, then there wouldn't be an argument. But obviously the argument is yes, if I want to measure the linear momentum, he's saying those are completely different numbers than the angular momentum.
this angular momentum, when this object is coming in, let's say it hits and sticks to it. We've got some initial angular momentum, and again, in my model, I'm not going to go into the full details on this, but this depends on the linear momentum of the object and how far it is from the rotation axis.
So this is where it all goes wrong. MVR. Because this is just squaring velocity again. It would be m times r. That's all you need. The radius is going to tell you what the velocity is. So this is basically saying mvv again, because the r is just going to represent an increase in velocity. You're at the same distance, it's 1. You go further, the further out you go, the higher the number goes, because you're increasing the velocity by that much. So the r just represents another way of saying velocity. And that's why that equation is obviously a kinetic energy equation, because it's squaring the velocity. You've got the velocity in there twice. The only thing the r is doing is changing the velocity. So obviously all you need is the r. You don't need the v anymore, because if you measure both the r and the v, you're basically saying the r doubled the velocity. Well, now you're going to multiply it times double the velocity. So you've just done v again, so v squared. So it's clearly not a momentum experiment. It's not talking about linear momentum. It's talking about linear kinetic energy.
So the ability of this thing to cause a rotation depends on how much momentum does it have and where on the bar is it hitting. If it's hitting further from the bar, it's going to be able to make...
How much momentum it has will be decided by where it is on the bar. Again, it can't have momentum until it's going to be pushed, and it's going to be pushed based on where it is on the bar. So the speed it's going to be pushed at is going to be dependent on where it is on the bar. The velocity is going to be dictated by the r.
Make that thing rotate more. And on the other side, after this thing starts to rotate, let me move down a little bit. Sorry that I'm going into a lot of detail here, but I do think it's important, and I'll try to keep it more brief than I have been keeping it.
Whatever. Again, and it's just a counter against my simple argument that all we want to know is we want to put energy in, and we want to see what comes out. We want to put movement in, we want to see what kind of movement comes out. We know the lever's going to move a little bit, so that's going to take some of the energy, and we want to see what the other object on the other side does in terms of moving. It's that simple an experiment.
So once this thing gets hit, mass 1 is going to slow down. It might not stop entirely. I know in one of your videos you were saying we don't want it to bounce. And the other object is going to be launched.
Yeah, and obviously the whole point of the experiment is stating, well, if you match these locations just right, then you will use up all the energy in the object, so it will stop, because you'll use all of its energy, because the whole idea is to give it to the other object. So you want to have a complete transfer. So you want to do nickels into dimes. You don't want to do something that's worth 3 cents into dimes, because it won't go in there in whole numbers. So you just try to figure out what the whole numbers are, 1/2, 1/3, 1/4, that kind of thing, and you'll end up getting an accurate conversion, a complete conversion.
In this case, my final angular momentum, well, it's whatever the final velocity of this object is.
So its final velocity is going to be completely dictated, okay, by whether you used all of its energy or not. So if you didn't use all of its energy, then it's going to still have motion. But if all of its energy went into the other object completely, because you put it at the right location, if you put it too close to the fulcrum, it's not going to be able to absorb the energy. The velocity is going to be too slow. So it's not going to have the full momentum. So you're going to have some left over, so it'll keep moving. If you have it at just the right location, it stops moving. And if you have this too far out, it's too heavy, and you'll get a bounce.
Again, I should have drawn this a little bit closer to the axis, so I should have drawn this close to the axis. There. Times that r distance. Plus.
So he's just done velocity times velocity, because the r distance is a change in the velocity.
The same thing for the launched mass. So this is m2 times whatever its final velocity is times whatever that distance is, plus any effect from the rotation of the bar, where this is the moment of inertia.
So there's no such thing. That's just the mass, okay? And that's it.
And this is the angular velocity, how fast.
And so that's just the momentum. So again, it's just a momentum term. How much is away and how fast is it moving? How fast is the average atom moving? It's all the pieces of its mass are going to be moving different speeds. So you're just saying what's the net average motion of a piece of lever. So you find the average speed of a piece of the lever and just multiply it times the mass of the lever.
So in this model, we can set these two angular momentas equal to each other. And
right.
I'm not going to go through the whole
So they're not angular momentas, they're angular kinetic energies. Just be clear. All you need is the m times the r. That's the momentum. Because the r is going to tell you what the velocity will be.
Because it takes a little bit. But if we have a case where m1 is equal to 2 kilograms, or just let's say 2 masses, because we're just going to say, double the mass. If m1 is 2 and r1 is 0.5.
I mean, theoretically, I suppose you could use r as 1 for any number that you start with, and then all the other relative r's on the other side would be a relative r. And then you're just going to use the relative change in the r as an increase or decrease in the velocity.
And m2 is equal to 1, and r2 is equal to 2. And we're assuming the bar is very light.
So mass 1 is the 2 mass, okay? And he's basically going to do this equation, and the result is just kind of funny because, frankly, he predicts wrong again.
So low mass bar, and that object 1 sticks to the bar. So there's no.
It doesn't stick, but it uses all of its energy. So all of its energy goes to 0,
bouncing off. So low mass bar, m1 sticks. The numbers I got are that the final velocity of object 2 should be 2/3 the initial velocity that this thing had before it hit the bar.
Right. So the heavy mass hits the bar, and he says only 2/3 of the velocity gets into the light mass leaving. When his own diagram, his own finished product, doesn't show that. So I'll draw what you'll recognize as the actual experimental data. Okay, and the experimental data was pretty conclusive, at least in this part, and in the experiment he did, is that you have the velocity of the heavy mass here. So this is the plus mass, the heavy mass. And obviously, when there was the transition from this going to 0 and the other one now is going to gain the energy, it clearly was more. So 2/3 would have been here. That didn't happen. M2, okay, the second mass, that's 1/2 the mass. That half mass didn't go 2/3 the velocity. It went 3/3 at least. 4/3, maybe 5/3. Okay, that's what it actually did. Now my prediction is it should go 6/3, right? It should go a full doubling of the velocity. Thirds, not halves here. It should do a full 2. This should go twice as fast. Okay, and it didn't. So this is missing off mine because he got the reflection here. So we got this reflection of the M2. So M2 didn't get all of its momentum into M1, but it always did more than 2/3. It always did more than 1. So he wasn't even predicting 1.4 here. He was predicting 0.7. So obviously that prediction was way off. Now you could argue he did his math wrong, but it doesn't matter. The prediction is clearly wrong.
It's not going to be double that value. It's actually only going to be 2/3. So there's a very significant difference between what your model predicts that the other mass should be.
So I'm just saying it completely failed to get the right answer here. Okay, the velocity of v of the second object, the half as massive object, the one that weighs 1 versus the other one weighing 2. Clearly, v2, the velocity of the second lighter object, was clearly more than 2/3. It was clearly more than 1. It was 1 point plus. So again, so just understand, he wasn't predicting 1.4. He was predicting 0.7.
Launched with
well, 0.666, right? He was predicting 0.66, and the outcome was clearly, 1 point plus.
Twice the initial velocity of mass 1, and mine, under these circumstances, it should only be 2/3 of the velocity of 1.
So he says it again, okay, completely wrong. Didn't turn out that way.
So if I apply this to a Newton's cradle, so you say in a Newton's cradle, if I hit a larger, twice as big mass with a half as mass, you're saying that I gain this 2/3, which is 133 more momentums.
So I'm giving a wrong example because I'm almost thinking 2/3, he means the heavy object goes 2/3. No, he means the lighter object only goes 2/3 the velocity. So it was way off. I mean, it was more than half off. I mean, it was way off, way under predicted.
Newton's cradle would be a little bit different because we don't have these R values. We're not conserving angular momentum for the Newton's cradle. We're conserving linear momentum for that one.
So as ironically funny as that is, right, when clearly this experiment's all linear because of the tracks, and the Newton's cradle is clearly angular, technically. Now, if you make the pendulum long enough, you can take a lot of that angular crap out of there. But it doesn't really matter because angular momentum is the same as linear momentum. There is no difference. It's all just about velocity of where the units of mass are. So if the units of mass, if that is the mass is on the outside of an object, it's technically heavier to roll.
I mean, that's just a qualification on the velocity. So we're just saying that the velocities are still the same momentum. So the rotational momentum has the same rules as the Newton's cradle. There is no kinetic energy correlate to angular momentum. So we would both agree that if the 5 mass on the outside will rotate exactly at the same speed as the 10 mass on the inside.
So we should disagree on that, and yet he disagrees with that. So Ian, do you believe that one? I mean, that's the experiment. You never got completely around to. He never got around to completely doing this experiment. But I mean, so again, we have another claim and an assertion. So we have another simple experiment. Let's see if someday somebody does the experiment, well enough. But I mean, it's a really simple argument. I mean, you got 2 wheels. I apply a mass, okay? So it's the same mass, one mass, and I just put those 2 masses at 2 different locations. So I put 2 of them here. Well, we could say 4 of them here, right? Yeah, that would be even better. So I put 4 of them on this circle, and then I just put 2 of them on this outside. Now the question is, now I have twice the mass here that I have here. Now in this example, will these 2 wheels roll the same? And my argument is, of course they'll roll the same, because all you've done is take the same momentum. This momentum will be exactly the same as this momentum. The momentum, double the velocity of these 2 objects with twice the velocity, all right, will add up to these 4 ones. So 4 ones equals 2 twos. And so they will roll exactly the same. They will take the same energy to move because, frankly, the atoms will have an average, the average weight, the average MV of the atoms. If I take all the atoms, including the weights, I take all the atoms, including the weights, the average mv is going to be exactly the same number. The average amount of weight the material has will be exactly the same with these two wheels. So they will rotate the same. Take the same energy to cause them to rotate, take the same energy to stop them from rotating, and they will roll at the same speed down an incline. Now that's my claim. I made it in 2 minutes or so. Can somebody explain how that doesn't happen? Can they show me the experiment that proves that doesn't happen? I mean, it's a pretty in-your-face, simple enough claim. And again, we don't have the experimental evidence, right? We can't go to the internet to find the experiment because nobody's done it. Which is, again, should be a glaring insufficiency to the completeness of this physics.
Two things will roll down a hill at the same speed because the angular momentums are exactly the same.
The angular momentums are the same.
So he's saying the angular momentums are the same. Well, then what are we having a conversation about it for? Then these are basically just levers. And so I've just proven that the lever with the heavy masses on the inside is the same as the lever with the light masses on the outside.
Sorry, the angular velocities are the same. But
now, obviously, the angular velocities can't be the same. I mean, obviously the velocity of the stuff close to the fulcrum, close to the center, it's moving much slower than the stuff moving on the outside of the circle. So obviously, the stuff on the outside is moving much faster, twice as fast.
Velocities are not the same. The 10 mass is half the r.
The linear velocities would be double. The angular velocity, the way I define it, is just...
So he's playing a game, The linear velocities would be double, so he's conceding that's the real measure of it, is the linear velocity. And now he's going to play some game about how much rotation distance it is, how much angular distance. Well, the angular distance doesn't have anything, it's not going to change anything either. In 10 degrees, this one's going to use the same energy as this is going to use in 10 degrees.
How many rotations does this go through per second? If they're on the same bar, it's going to go through the same number of rotations per second.
Well, they can't be on the same bar frankly, if these two objects are in the same bar, I could put two different objects on the same bar. Then I'm going to force the two of them to compromise. Neither one of them is going to do what it wants to do because the other bar is going to change how fast it can or can't go. But they're not going to match. So you're just saying, if you match them, then it's going to be the same. But if you don't match them, it's not going to be the same. But they're not attached. The whole point is does it take the same energy to move both these wheels? And the fact is it does.
That's what I mean by this angular velocity.
Again, it doesn't make any difference. I'm just saying, so you don't agree that if I make a wheel and I have a 5 mass on the outside of the wheel and I have a 10 mass on the inside of the wheel, they're two different wheels. One with 10 mass on the inside, 5 mass on the outside. You're saying that they will rotate differently.
Yes, absolutely.
And so there's a claim. Now, Ian, it's a pretty dramatic statement, right? I mean, we have definitely opposite opinions, and it really relates to levers because, frankly, it's the same experiment as a lever.
I'm saying that there's a ton of physics videos where they roll these objects, hollow objects versus filled objects. How could it possibly have more angular momentum? It's a 5 mass moving twice the speed of a 10 mass moving half the speed. How could they have different angular momentums?
Because for a rotating object, this moment of inertia depends on how much mass there is and where that mass is located.
I just said that. So we know it's half the mass at twice the distance. So it's twice the r and half the velocity. So if you multiply half the mass half the velocity times the r, then you're obviously going to get, the two numbers are going to compensate for each other. If I say increase r, I'm decreasing velocity. I'm increasing velocity.
Located relative to the axis, and for a single object, this is actually m times r squared. If it's further away, it has an additional effect.
So again, he just says so. There's just no evidence, and r squared would be a preposterously huge number. I mean, now you got velocity squared, which would make no sense at all.
You're muted right now. You're muted. We can't hear you.
You're using the kinetic energy version, so you've just created a kinetic energy version of the very thing you said right down here. LP equals MV IPR plus blah blah blah. So you've changed it to squaring now. You're squaring the velocities.
I'm squaring the distance that these masses are from the rotation axis.
Right, and for what? How could that possibly work? I mean, how could I possibly make sense of that? That's saying that this is going to take twice the energy to move when it's half the mass. How can half the mass be twice the energy to move? I mean, again, it doesn't make any sense. The lighter thing has more inertia. The lighter thing has more resistance to motion. Again, what sense does that make logically? So I have played some of this, all this before, so I don't know if we need any more of this. I could go a little further, right? It's not going to hurt any. A little bit of redundancy won't kill you. But just understand the 2/3 he's got written there. You can see that, right? 2/3 the velocity. That was wrong. Wrong predicts. Way off. Way off. In none of the experiments did that 2/3 show up. Wrong button.
Okay, you're squaring the r. It doesn't matter which one you're squaring, really. So I'm just saying you're squaring one of the numbers. So frankly, it's two different formulas.
For the math,
See, it doesn't really matter whether you square the velocity or square the r, because they're both doing the same exact thing. The r creates the velocity, and the velocity is going to be a product of the r. So it doesn't matter which one you
it
square.
very much matters which one you're squaring, because again, we want to be very, very specific in what values we're looking at. And again, this is another point of disagreement between us, because you seem to argue, and again, correct me if I'm wrong, you seem to argue that momentum, force, mass, a lot of these energy, all of these things are essentially equivalent to each other. And in my model, there are very, very important differences between those.
I don't know what those would be, so it would be interesting for somebody like Ian to make a video explaining what the differences is. That motion is somehow different. So if I have a big object moving like the Earth made of a ton of little electrons, it's somehow, the fact is I can't take one of those electrons and put it outside the Earth and it'll do exactly what the Earth does. It'll orbit the same, it'll be doing exactly the same thing. And yet somehow there's a difference. Heat is just mass moving. There's nothing else. Everything you can describe as energy is just masses moving. And all you have to do is calculate how much mass and how much velocity. And that'll tell you how much energy you have. You just add up all the MVs.
I'll go back to the original argument made by Leibniz. Okay, this was an all or nothing argument. It wasn't any semantics argument. It was a real argument about one is real, one is fake. So I'm just saying there's no point in having the word momentum anymore if kinetic energy is true, because there's no reason to conserve it. There's no reason to care about it because it doesn't mean anything, and vice versa. Frankly, I mean, one of them has to be real, one of them has to be fake. You can't have this duality.
I would disagree with that position.
Yeah, so again, I can't see, there's no possible way, again, they keep saying it, and it's just so wrong. They have to concede this is a real mathematical problem. That there's no logical reason. Okay, I have a 5-ton train going 10 miles an hour. I add 5 tons to the train. Now I've added it through gravity, which means I've added energy in the downward direction. So any vibrations are going to be created by the gravitational energy. I'm not going to steal from the motional energy. So that's like making an argument in shooting something off of a cliff. You're not going to change how fast it's falling, and you're not going to change how far it goes. The air will, but the two forces aren't going to affect each other. This downward force isn't going to affect this forward force, so the two are irrelevant. But the point is I can find subtle ways to drop this, connect this weight. And once connected, now it's going half the velocity. That's the concession. It loses a tiny bit of momentum, a tiny percentage of its momentum. Now it's a 10-ton train going 5 miles an hour. So it didn't lose any momentum, and yet it's lost half the kinetic energy. You have to understand that that's a mathematical necessity. It's not a physical necessity. There's no evidence that half the energy went anywhere. It's just a mathematical statement saying, well, because you've increased the mass, okay, and decreased the velocity, you've decreased the squared term, and you've increased the not squared term. So obviously you're going to have a mismatch. Again, I mean, how many times do I have to say it? You really believe I can take something with a certain momentum, change it, but conserve all of the momentum, and yet I can release half the energy into the environment somewhere. So even though I didn't use any of the momentum of the object, I can create an amount of energy equal to half its momentum. I can let it loose into the environment somewhere, and I didn't have to use any momentum to do it. It's like saying I can hit the bowling pins with the bowling ball, and the bowling ball doesn't go any slower. You can't do that. The bowling ball has to lose its energy for the pins to have energy. That's the elemental physical concept you're disagreeing with. You don't agree with that simple statement.
Let me give you an example of why I disagree with that. We're going a little afield, but let me just kind of finish this part by saying I can make a prediction. With my model, I'm making a prediction about how this experiment should go.
Right, and the prediction was wrong, proven wrong. So the first prediction was half and half. That was wrong. The second prediction was 2/3 the velocity. That was wrong. Profoundly wrong. Not a little bit off, way off.
A prediction, and I've got a prediction, and eventually the experiment will kind of highlight those differences. Let's say we agreed on this equation for conservation of momentum in just a one-dimensional collision. One object runs into another, and either they stick together or they bounce off of each other. They do something. We agreed with this one, right?
Yeah, all the energy stays in one of the objects. It's an elastic collision. All the energy has to be in one of the two objects. If you can't turn it into something heat, if you can't turn it into pieces flying off, if you can't turn it into sound, you can't turn it into something else, it has to stay in the two objects.
Whatever, just go ahead. I'm saying yes, I'll agree that the only thing in the experiment are these two objects. We're just trying to, let's say they're in empty space, and we're going to figure out what happens to them.
Okay, so my point here is that conservation of momentum gives us this equation, but it is not sufficient to figure out exactly.
All right, well, this is just the gibberish where they say somehow we can't do the experiment and find out the answer. Instead, we have to do an equation. And we have two unknowns and only one formula. And we need two formulas for two unknowns, and this kind of nonsense. So they fuck the whole thing up by marrying momentum to kinetic energy, and they create a Frankenstein formula out of those two formulas. So they basically set it up to say mv equals 1/2 mv squared, when obviously it doesn't in every case where you change the mass.
How these objects are moving. Because if I have these two final velocities, if I have only one equation and there are two unknowns.
So again, it's just you just said you had the velocities, you had the masses going in. If I have the velocities, so it didn't even say it right. Well, if you already have the velocity, if you measured them, then you don't need the formula anymore, do you? No, you can just plug it right in right here, and you got the answer, no problem. It's if you don't know the velocities, you need another formula. But again, why is predicting more important than actually doing? Why not just measure the outcome? Well, anyway, too ridiculous. All right, so enough of that. I haven't checked to see if physicist Michael responded to the silly John Walker crap about gravity. Absorbing the momentum of the anvil is somehow compensated because the ball bearing attracts the anvil towards it. You see, and so that's undoing its momentum. So it gets momentum each time the ball bearing hits. It gets momentum, but the momentum disappears because the ball bearing flies up and it pulls the anvil back up again. We don't have a response to that idiocy. So, all right, enough of the video and such and so forth and whatnot. It's just crazy, right? That this argument has to exist only because a pitifully poor science never has done these experiments. They've never taken a lever and analyzed how it works. They've never taken it into a laboratory and dissected its function. And that's the physics you trust. They've never done the experiment. Amazing. Fucking amazing that you fall for this crap.